This presentation is about semiconductors, and we'll try to understand some of the underlying concepts like bands and gaps. Semiconductors are materials which are neither good conductors like copper, gold, silver, metals, nor are they good insulators like rubber or glass. The most commonly talked about semiconductors are silicon and germanium. Silicon lies directly under carbon on the periodic table, and germanium is under silicon. So here we see the position of silicon and germanium on the periodic table. Much of a computer circuitry is made up of semiconductors. Before we had semiconductor transistors, solid-state transistors, we used vacuum tubes, and they were quite large. So the ENIAC was a computer made up of vacuum tubes. So in addition to the obvious benefit of taking up less space, the devices, now smaller because we're using transistors, tend to be faster and require less energy. So here we see pictures of the ENIAC. So we can see that it fills an entire room, a rather large room, and it was one of the first electronic computers built in Philadelphia in the US during World War II. It has only like 20,000 or so units, vacuum tubes, so its computing ability was quite modest compared to what we're used to today, and it used a gargantuan amount of power. So if semiconductors are neither good conductors nor good insulators, then why are they useful? What makes them useful is that they can be manipulated, that a semiconductor can be made into a somewhat better conductor, and it's this control over their conductivity that makes them useful. Also, the semiconductor is not ohmic, it's not linear. So the resistance offered by the semiconductor can be changed, and this is going to give them their sort of on-off quality that we can incorporate into our logic circuits. They can also be used as detectors, so they can depend on external things like how much light is shining on them, and then that can make them detectors that can be used in scanners and photocopiers and laser printers and digital cameras and so on. The main way to change a semiconductor's properties is to dope it. So you have the semiconductor, the pure semiconductor, say silicon, and then you dope it by adding some substance, some chemical, and usually it is an element from either side of it on the periodic table. So those elements are sort of close to silicon, but not quite silicon, and that little bit of difference is known as doping. So here we're looking at a close-up of silicon and germanium in the periodic table, and we notice some of the neighbors, aluminum and phosphorus on the same row as silicon, gallium and arsenic on the same row as germanium. One of the reasons the periodic table is a useful sort of organization of elements is that elements are largely controlled by the electrons in the sort of outer shell, what we call the valence electrons. And so when you dope with elements on the right, you are increasing the number of valence electrons, and this is known as n-doping. If you dope with elements on the left, you are decreasing the number of valence electrons, and this is called p-doping. The material you add is known as the dopant. And either way, either kind of doping, whether it's with N or P, actually improves the conductivity. We'd like to see why. It turns out that the electrons that are surrounding atoms cannot have an arbitrary amount of energy. They end up in these very precise energy levels. You might recall, if you've studied chemistry, the sort of 1s, 2s, 2p, the so-called orbitals or energy levels. So this is what they were talking about. And the energy is said to be quantized. That means it has to have these specific values, and it can't be general, any arbitrary amount, but it must be these specific amounts. That's what we mean when we say quantized. So the individual atoms had these energy levels, and now we're going to bring a lot of atoms together. So we're still going to have these quantized energy levels, but we're just going to have a lot more of them. So now we have the first energy level of atom 1 and the first energy level of atom 2, etc. And they're going to affect each other a little bit, and maybe one energy level will go down a bit and the other one up a bit. And so, but there's going to be a lot of energy levels close together, so it's almost continuous, or what we'll call quasi-continuous, and this closely packed set of energy levels are what we call a band. So again, we started with atoms which had these energy levels, these discrete energy levels, these quantized energy levels, and so most energies we're not allowed to have. There are only a few very precise energies we are allowed to have. Then we brought the atoms together and we had many sort of overlapping energy levels that affected each other and spread out a little bit into bands. But there are still energies we're not allowed to have. So even with the spreading of the energy levels, when you bring the atoms together, there are still energies we cannot have when we are done bringing the atoms together. These are known as the gaps, band gap or just gap. So again, we start with our picture of our isolated atom. It has its discrete energy levels, its quantized energy levels, and most of the energies we're not allowed to have. Now, it doesn't mean all these energy levels are full with electrons. There are only electrons in some of these levels. These are just the levels that the electron is allowed to move to. Then we're going to bring those isolated atoms together to form a solid. So then these energy levels of the individual atom sort of overlap and affect each other and form these bands, but there are still places, energies, that you're not allowed to have. These are the gaps. And just like in the atom, not all the levels were full of electrons, the same thing is true over in the band picture. We are going to have some of the bands full or half full or all the way full, but not all the bands full. And this is going to be important in our consideration of what makes a semiconductor. With both our isolated atom as well as with our solids with their bands and gaps, what's important in terms of levels or bands is whether or not the levels in them are occupied. Are there electrons there or not? And so now we need to understand sort of the rules of occupation. So electrons are said to have a property called spin, and spin can have two values, up and down. Then there's a principle known as the Pauli Exclusion Principles that says two electrons with the same spin cannot be in the same level. Therefore, at a given level, you can only have two electrons, provided that they have opposite spin, one spin up and one spin down. We imagine the following, that we've brought the nuclei together and we've formed these energy levels, and that they're all empty, and now we're going to start bringing in the electrons, and you bring in the electrons sort of two at a time, one spin up and one spin down, and then the first two electrons will go in the very lowest level. Then we will bring two more electrons, again one spin up and one spin down, and we'll put it in the next lowest level and start to fill up, and this will make the sort of lowest possible energy of the solid as a whole, and this will be known as the solid's ground state. So in this imagined process, we've brought together the nuclei and they formed these bands of energy levels, and now we're going to fill them up with electrons, sort of two by two, a spin up, a spin down, filling the lowest energy level. Well, where does it all end? Well, how many electrons do we have to put in? We have to put in enough electrons. The nuclei were positive. We have to put in enough electrons to make it electrically neutral. And so we are taking our electrons, enough electrons to make it electrically neutral, and putting them into these levels within these bands. And then where does that process end? Well, it ends when it's neutral, but where in the band does it end is an important question. If we end up to be in the middle of a band, we have a metal. And if we, in the filling process, if we end up at the top of a band, then we have a semiconductor or an insulator. and that's determined basically by the size of the gap between that just filled band and the next. This is a bit oversimplified, but this is the basic idea. Okay, but what does this all have to do with conductivity, the ability to move charges around? So we've filled up our levels with the spin up and the spin down, and we've filled up to the ground state. And we can think of it as having as many electrons moving to the left as moving to the right. Now we would like to introduce a current. We'd like to have a net current, not as many moving to the left as right, but say more moving to the right, for instance. And so we've got to move these electrons into higher energy levels so that we can get more moving to the right than to the left. So we need a little bit of energy to move them into these high energy levels. Now the electrons sort of down in the pack within the band, all the energy levels near them are already full, so they're not the ones that are going to move. It's the electrons that were near the top of the band. Those are the ones that have a chance of moving. So we started with our energy levels and we brought them together to form a solid, and then those energy levels formed bands, and sometimes there were gaps between the bands, and we filled up the levels with the electrons. And now we want to talk about conducting, to move the electrons around, and so they need to be able to move into higher energy levels so we can get more moving to the right than to the left. So if we are at our highest level, the highest level is known as the Fermi level. If our highest level of the ground state, the Fermi level, if that's within the band, then there's this quasi-continuous set of energy levels nearby, and so we can easily get to close by other levels and get this sort of net current going in one direction. We're a good conductor. If the Fermi level, that is the highest level of occupied state in the ground state, if that falls out of gap, then we need a lot of energy to get the current, because the current requires us to move into high energy levels. And if if the next unoccupied level is a gap away, then that's going to take a lot of energy. And if it's a smaller gap, semiconductor. If it's a large gap, insulator. So we have many energy levels forming bands, and then we have gaps between the bands, and the Fermi level was the highest occupied level. If the Fermi level falls at a gap, then we talk about the level below it is filled and is called the valence band, and the level above it is unoccupied and known as the conduction band. And electrons will have to go from the valence band up into the conduction band, sort of getting enough energy to leap over the gap in order for there to be a current. So in the picture on the right, we were filling the band, the lower band, with electrons, and 2 by 2, one spin up, one spin down. And then when we got to the place where we had enough electrons for the solid to be neutral, we found that we had just filled that band, and that made it the valence band, where the highest electrons were. And then the conduction band was separated from the valence band by this gap. That's our main idea behind what makes something a semiconductor.